Okay, so I wanted to go ahead and just do a brief screencast on some of the stuff that you talked about Friday when I was absent with my graduate student, Harry Kotapati. So all of this he's already gone over with you, but I just wanted to do my own screencast, so in case there was any confusion about any individual pieces of the lecture. So on Friday, you talked a little bit about alkyl halides, and you got started about talking about nucleophilic substitutions. And so this is the chapter where we really start to talk about organic reactions, how we convert one organic substance into another. And substitution reactions are a big part of that. And so you'll recall that alkyl halides are organic molecules that contain a halogen atom bound to an sp3 hybridized carbon. So if the halogen is attached to a methyl group, we call it a methyl halide. If the halogen is attached to a primary carbon, we call it a primary alkyl halide. If the halogen is connected to a secondary carbon, we call it a secondary alkyl halide. And if it's attached to a tertiary carbon, we call it a tertiary alkyl halide. And here, X is just an abbreviation for fluorine, chlorine, bromine, or iodine, and that's a common abbreviation in organic chemistry. So pretty much so anytime you see X, you can think of a halogen in general. So some examples here you can see we have a primary alkyl iodide. Here we have a primary alkyl, or a secondary alkyl bromide. And here we have a tertiary alkyl chloride. There are also other types of halides that we can have. For example, we can have a halogen attached to an alkene, which becomes known as a vinyl halide. And we can also have a halogen attached to an aromatic ring known as an aryl halide. And notice both of these carbons are sp2 hybridized carbons. And these halides are actually unreactive in nucleophilic substitution reactions, which is what we're talking about in this chapter. We also have molecules where the halogen is attached to what's known as an allylic carbon. So if you look at this particular carbon here that I'm got my cursor on, that carbon is directly attached to an alkene, and so this is known as the allylic position. You need to know that. And so when we have a halogen attached to that allylic carbon, we call it an allylic halide. Likewise, we can have a carbon that's very similar to an allylic halide, except instead of being attached to a normal alkene, it's attached to an aromatic ring. And we call this position the benzylic position, and so these are benzylic halides. These reactions, these substrates, because they are attached to primary alkyl halides, if you will, are capable of participating in nucleophilic substitution reactions. So the naming, you're just going to treat the halogen as if it were a typical substituent. And so all the rules that you've learned about before apply, except that now your substituent for chlorine will become a chloro, a bromine will be a bromo, so on and so forth. There are some common names, however, that you should know. For example, the one that you see here, this is known as tert-butyl iodide. Okay, the IUPAC name would actually be a propane derivative, 2-iodo 2-methyl propane. But the common name is to treat it as if it were almost like a salt. So tert-butyl iodide. Here we have an ethyl group attached to a chlorine. That becomes ethyl chloride. You went through your concepts test with Harry, and I hope he showed you the answers. But I've got them for you here, and you can see that the halogens just become substituents like any old substituents. They don't have any special preference. Physical properties with alkyl halides, of course, because there's a polar bond, as you can see in the picture, you're going to have a situation where the electronegative halogen atom is going to pull electron density to itself and create a dipole within the molecule. So alkyl halides pretty much so have dipole-dipole interactions as well as van der Waals, of course, just as everything does. And this does have some effect on the various physical properties that we see. So for example, ethane has a boiling point of nearly minus 90 degrees Celsius, whereas ethyl bromide has a boiling point of 39. So the dipole-dipole interactions do play a role. Alkyl halides typically are soluble in organic solvents, and they're typically very insoluble in water because they typically don't form hydrogen bonds. There are some common alkyl halides that you all are already familiar with. For example, the one that we have up here, PTFE, also known as Teflon. This is what's used for a nonstick coating, and you can see that all of the carbons are either attached to other carbons or fluorines. Makes for a very nice nonstick coating. We coat our pans and utensils with that so that food doesn't stick. This is polyvinyl chloride. You can see the green spheres here represent chlorine, and PVC. You probably know this as sewer pipe or water pipe. Very good for making those types of materials. This molecule right here, CFCl3, also known as Freon 11, is used in cooling systems. And then this molecule right here, DDT, which was used for many, many years to treat mosquito populations, has since been banned because of the effect that it had on wildlife, especially in this country, the bald eagle. But you can tell it's got a lot of chlorines. Chloromethane is a very simple alkyl halide. It is a natural product in the sense that giant kelp and algae emit this as a byproduct of their biological processes, and it's also results in emissions from some volcanoes in Hawaii. Dichloromethane here is a common organic solvent that you all will use in organic chemistry. It's also known as methylene chloride because, of course, the CH2 is a methylene group. And this at one time was actually used as a solvent to decaffeinate coffee quite frequently. And then halothane, shown here, is a general anesthetic that has overtaken the use of other anesthetics in recent years because it is relatively safe compared to, let's say, ether, which is highly flammable. Halothane is not as flammable, and so has a lot of potential benefits there. As you can see, the polarizability of the bond also comes into play. If you look at methyl fluoride, methyl chloride, methyl bromide, and methyl iodide, you can see that the bond length between the carbon and the halogen increases as we go down the periodic table. And so, as you might imagine, the CF bond is actually quite strong, whereas the CI bond you can consider it to be quite weaker. And so you can imagine in these nucleophilic substitution reactions that we'll be discussing that the reactivity of these alkyl halides increases as you go down the periodic table as well. So here we go, starting talking a little bit about nucleophilic substitution. And so if we have an alkyl halide which reacts with a nucleophile, we're going to get a new carbon nucleophile bond, and the halogen leaves away, and so we call it a leaving group. This is a common reaction that alkyl halides undergo. Very, very important to note here that a nucleophile, by definition, is a Lewis base, and there is a rule that I want you to know. I want you to know that all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, and we'll learn more about that later, but that's something you need to commit to memory. Another reaction that we'll talk about later that alkyl halides readily undergo is elimination. So what distinguishes a base from a nucleophile? Well, that's what I was talking about. There are conditions where the base just won't behave as a nucleophile and displace the leaving group, whereas in a nucleophilic reaction it does. And so we'll learn as time goes on more about the differences between nucleophiles and bases. So let's look at some examples. We have chloromethane reacting with hydroxide. Hydroxide is the nucleophile. In this particular case, the arrow would be a double-headed arrow going from the lone pair of electrons on hydroxide to the carbon of the methyl group, and would also have an arrow going from the bond between the carbon and the chlorine to the chloride. And so here we have a functional group transformation where we are converting an alkyl halide into an alcohol. We also have the same reaction where we take a thiolate and react it with an alkyl iodide in this particular case, and we get a mercaptan or a thiol. And we can also see that we can take an alkyl halide and convert it into an ether. And this process is known as the Williamson ether synthesis. And you need to start memorizing some of these name reactions. And the Williamson ether synthesis is the first one that we come to. But notice here how the arrows are shown in red. And that's exactly how this occurs in all three of these examples. And so we call these functional group transformations. Notice we can go from alkyl halides to alcohols, alkyl halides to thiols, and alkyl halides to ethers. And so this is a very important time for you to start actually building these roadmaps where you think about things that we can do to functional groups through reactions. And I'll show you another example of that in class on Monday. So I'm going to skip through this real quick. Harry talked with you about this. The leaving group, of course, is very important. And we know that as we go from left to right on the periodic table, we're going to increase the ability of the group to leave. So water is a better leaving group than ammonia. And so you can imagine that a halogen will be a better leaving group than an oxygen in some cases. And if you look at the halogens, we see that as we go down the periodic table in the halogen family, leaving groups get better. And that goes back to that previous slide I showed you where the bond length was quite long for an alkyl iodide, for example. And this seems to follow the basic character of the anion. So weak bases actually make better leaving groups. That's what you need to know. So iodide is a weaker base than fluoride because HI is a stronger acid than HF. And so here comes that acid-base chemistry again. So we just need to know that weaker bases make better leaving groups. So if you look at all the good leaving groups, if you will, so water is a good leaving group, iodide's a good leaving group, bromide's a good leaving group, chloride's a good leaving group, and what you'll notice is that the pKa's for the conjugate acids, they're all strong, right? They're all strong acids, meaning that the leaving groups are very poor bases. And so the better the leaving group, the poorer the base will be, if you want to think of it that way. Now, if you look at here, alkyl fluorides, fluoride is the leaving group, the conjugate acid is HF, it's actually a weak acid. And so again, that means that fluoride's a relatively good base, and so it's actually a poor leaving group. Fluoride is not a good leaving group under most conditions. Nor is hydroxide, nor is NH2-, nor is H-, nor is carbon-. All of these are actually considered to be poor leaving groups. But chloride, bromide, and iodide are actually quite good leaving groups. So we will start on Monday by looking at these reactions. So I want you to think about these reactions tonight, and we will go over those first thing in the morning before we get started on the next set of slides in Chapter 6.